Okay, let's see what we can talk about with weather forecasting. You learn tremendous amount of all the different variables, how they interact, how storms develop, how tropical systems develop. So now we're going to try to put it together and look at how we forecast weather. In order to forecast the weather, you got to know what it's doing first. So, for example, over the ocean, we have some ships that report, buoys, aircraft might pick up some things, satellite might be able to do some observations for us, even radar. Over land, we'll have some upper air stations. We'll have a lot of surface stations. Just about every airport in the country has one. We'll have satellite images again, radar, and we also even get aircraft. Aircraft provide temperatures as they take off and land and altitude they are. Many aircraft give that information. And they also provide wind information. So you get more and more complete picture of the weather. Oh yeah, GPS satellites, actually. We can have stations that actually monitor them, pick up wind direction, and pick up precipitation or actually humidity changes within the atmosphere. Because the timing of those waves, radio waves and all, are different depending on the structure of the atmosphere. And that small bit of timing can provide information. So with that, we need them from all over the world. So we do have international cooperation on that. That's one area at least everybody seems to work together on. This is a typical National Weather Service office. Here's the radar. Here's a big antenna, satellite feed coming in. Tons and tons of data come in. All kind of numerical models, all kind of satellite data. I've been showing you just a small sampling of it. But these are located, there's 122 of them located throughout the United States. I was in the one in Wakefield. I also served in one in Sterling, Virginia. In Ohio, there is one near Cincinnati, just outside Ohio, that area in Cincinnati. There's also, actually, it's called Wilmington, Ohio. Then there's Cleveland, Ohio, that has one. Pittsburgh, Charleston, West Virginia, Louisville, Kentucky, all actually do a portion of forecast within Ohio at times. So here's an example of I talked about surface observations. Here's ASOS. ASOS is just at most airports now. The FAA maintains a lot of them. The National Weather Service maintains some. And even the Navy and the Air Force get into the pack. So you can see them all scattered around the country there. You think about it, though, that's a lot of dead space between them. Over the ocean, you have the National Buoy Network. Cooperative stations give you a lot more information. Radiosondes, not a lot actually go up. Here, here's your map of them. Notice there's, again, a lot of holes in the data. Well, we've talked about surface weather maps and all. So here is a surface weather map zoomed in, and I defy you to tell me whether this front is down here or is it up here in this part of Ohio. And if you live here, that can be kind of important for your forecast. But there is very, very few observations there. We can infer some things by looking at these other observations. We can estimate. But like you, if you were driving from Mount Vernon to Columbus, as I said before, you might pass through a front along that way. One side of it might be very cold. The other side might be relatively warm. We can't pick out those because we don't have enough observations for that. It's something the Weather Service and meteorologists are always going to screen for, is observational data. Another area, this is down towards me. One of the things we don't have a lot of are observations over the Chesapeake Bay. That's a pretty big body of water there. So if you were boating on it, you'd want to know what the winds were, I think, what the waves are. But we only have one observation here. You got to go all the way down here before you get another one. So if you're in this part of the bay, it could be a big difference in winds in that area. Again, we can infer some things. And look, if you're out in the Atlantic, this is the closest observation to Virginia Beach. So all this area here, you have nothing from it. So this is the big point with observational data. Now, all these observations got to be put in, and they develop weather maps and upper air soundings and all that we've looked at throughout the course. They're all put into a system called AWIPS. I actually was in charge of AWIPS at our office for years, and what it really does is provide you a means of looking in detail at weather across your area. Radar screen showcased here. Different 4-panel images of the weather, maybe looking at 4 different elevations. All things on the other panel might be looking at surface observations. All these things can be combined together to develop the forecast that the meteorologists are giving you. Numerical weather prediction. We've talked about it at times this course. Every one of those variables do have an equation attached to them. If I wanted to know what the wind was, there actually is an equation that I can determine exactly what the wind should be. I can't solve that equation, and that is a lot of the problem we have. Since we can't solve them, we got to do approximations, and we've gotten very good at it. But there are approximations over a global scale called the global forecast systems. There are approximations over more of a smaller area. The North American mesoscale model is that one. And we can look at high resolution, the HRRR, high resolution rapid refresh model, which literally comes out hourly. The NAM comes out every 6 hours, as does the GFS. So, and there's a European model, there's a UK Met model, there's a Canadian forecast model, all of which, if you want to, you can get access to. So, with that, let's look at a tropical model. We have the Hurricane WRF. It's similar to the NAM, except it's specialized for hurricanes. This is a surface pressure wind field forecasted Sunday evening at 8 p.m. And you'll notice ISIS is just off of the Florida coast there. And pressure is about 992, 989, something like that. You can see there's a 50-knot wind here on the eastern side. Some other ones. Winds aren't too strong over the area of Florida at that time. So this is its forecast. Here's Wilmington, North Carolina. This is Monday evening at 8 o'clock, and it's right off Wilmington. You can see some 50, 55 knot winds down here, which is equivalent to about 60, 65 mile an hour. Off the, mainly on the ocean side, think about it, friction is going to be pulling them a little less on the land side. If you were looking for storm surge, remember we talked about it last time, where it'd be right in here where all these east winds are coming in. Not a very big one. Winds aren't that strong, and they're not coming over a large area. And finally, you can look at this 6 hours later, and it's coming up towards me. Notice the Chesapeake Bay here. Southeast winds on the Chesapeake Bay. If I lived up towards in this section of the river here, I'd probably be looking at higher tides. And this is by 2 a.m. in the morning on Tuesday. And then it's north of me. And look on the backside, 30 to 40 mile an hour winds here, maybe even some gusts of 50, but diminishing. So it's a very short-lived event. This is an ensemble of the same exact thing called the North American Ensemble. It looks at GFS ensembles, Canadian ensembles, others. Here is a forecast where the low is. Here's the spread, and you can see there's a pretty good spread to the east of where there's different pressures at, differences. So it really has a lot of difficulty estimating exactly where this storm is going to go, whether it's going to be a little bit more to the east, a little bit more to the west. So that's why that cone uncertainty and all is something to really look at. One other thing I did want to show you today is looking at just a high resolution model. And if we look at it, we can bring it into the U.S. Northeast. One of the nice things about the high resolution model is they can simulate radar images. So they can actually, if you're interested in what the thunderstorms are doing in your area or what they might develop like, this is a model that's run literally hourly, so it can pick up on things fairly quickly. And you can see there's a lot of showers and all over here moving north across Ohio at this time. Thunderstorms in here, some of the heavier showers, and more of them back here. Oh yeah, look at them all down here over the Carolinas have developed as well. Now they're moving up in towards my house, a little bit of them. So this is a great model for literally looking at every 15-minute timing. And if it's really doing a good job, you literally could time a picnic between the showers based on this model. So you can see there's various models that contribute to the forecast that you see. And the final thing is, if you look at a forecast and the Weather Service puts out, they're all high resolution. And if you go down, you can actually get an hourly forecast. We are literally forecasting nowadays for 2.5 kilometers and an hourly weather at that site. So say I wanted to know what it was looking like somewhere close to Mount Vernon here. I could click on that and I would get a forecast for that time frame here. But I can also get this wonderful hourly weather map, weather forecast that literally is showing me how the temperature is going to change and the dew point. Oh yeah, and it also shows the winds and then the amount of probability of precipitation, relative humidity, sky cover. So pretty much everything we've talked about in the course, we're forecasting if you're a meteorologist at the Weather Service for you every day. These are updated whenever needed. You're guaranteed to have an update at least every 6 hours in the system. So you can see all kind of new stuff here that you haven't maybe even thought about. All the Haynes index and all are fire weather indexes, lightning activity level. So this is where everything you've learned about is coming together now to write a forecast. So hope you enjoyed a little bit of this, and next week we'll just start talking about climate for a week.